In this module, we'll consider electric potential energy. As we know, it can be difficult to calculate work across a various path because the work can be path dependent. There are special forces, forces whose work is not path dependent, that are called conservative forces that we learned back in Chapter 6. For non-time varying electric fields, that is, electrostatic problems that we're dealing with right now, the electric force on a test charge is a conservative force, and therefore calculating the work can be done on any path you want between 2 points. So if you're calculating from point A to point B, to point B, let's say, and let's say the charged particle took this path, then you could solve for the electric force here. Let's say it's in this direction, and the small delta x here. And then you could go to the next point along the path, say up here, and calculate whatever the force is. Maybe it's like that, and the new delta E, and so on and so forth, and calculate the work. But because it is path independent, it is possible to take other paths, such as maybe this path, and you should get the same answer for the work. It is path independent. It only depends on the initial and final spots. If you forgot that, go back and look in the chapter on work and energy. Now, when it is path independent, people can work out and give you a formula that depends on the path, on the initial point in space and some reference point. These are called potential energy functions. So you can calculate the work, and usually do calculate the work, by calculating the change in potential energy. From Chapter 6, the definition of that was that the change in potential energy, in our case the potential energy due to the electric force, is minus the work done by the electric force. So we could take the stuff we did in the previous video for work, and we could calculate the change in potential by just putting a minus sign. But that's kind of doing it backwards. What we want to do is develop a way to measure the change in potential energy, which we'll do eventually by developing a new concept called electrical potential. Take the negative of that and use that to calculate the work. Again, this is definitely equal to Q times your electric field dotted into small displacements across some path. But this is the key thing right there. Change in potential energy is minus the work of a conservative force, and the electric force is a conservative force. Now, potential energy is not a scalar field. And the reason it's not a scalar field is that it depends on the charge of the test object. Remember, a scalar field is something where you have a function that only depends upon space and possibly time. Since we're doing time-independent problems, they should depend only on space. So for a given place here, let's say right there where that blue dot is, it should have a single value. And for a scalar field, that should be a scalar value. But our equation right here says it depends on the charge. So if you change the charge, you change the potential energy. Well, this is because the potential energy doesn't belong to the charge. It belongs to the charge and the field, which was set up by other charges. Let me give you another example that in terms of something you're more familiar with, gravity. If you take a mass here and you raise it some height, h, and you define this to be y equals 0, the potential energy is mgh. It doesn't just depend on the spot. It depends upon this mass. So the value would be different depending on what mass you put there. If you put an elephant over here, it's got a lot more potential energy stored than if you put a paper clip. Now what we can try to do is to get rid of this dependence on m. That is, we could define a new quantity, u divided by m, and that would be GH. The only thing in here are things that are the same at a single point of space. Potential energy divided by the source, in this case the source of the gravity is mass, is a scalar field. We want to do something simpler. We want to take electrical potential energy and we want to divide out the source of that electric, which is charge. And we want to define that as something. And what we're going to define that to be is what's called electrical potential or voltage. That's the goal in the next video.